Late in 1895, in a little university laboratory in Bavaria, Professor Wilhelm Conrad Röntgen first noticed the strange effect which led to the announcement of his discovery of X-rays. And although the news was received by the public with a mixture of disbelief and apprehension, doctors immediately saw the possibilities of the mysterious new rays and began to use them. It was not until 1913, however, that their use became certain and reliable. In that year, the hot cathode X-ray tube was introduced by Dr. William D. Coolidge of the General Electric Research Laboratory, the man who had already developed the all-important ductile tungsten lamp filament, and who now holds one of the world's few honorary degrees of Doctor of Medicine. In speaking of X-rays, therefore, it is a privilege to be able to present Dr. Coolidge himself.
For a long time, after X-rays were discovered and used, they remained a mystery even to the scientist. That is how they got their name, X for the unknown. Today, however, we know that X-rays are a form of radiation belonging to the same family as light, heat, and radio waves. We know also that X-rays are produced whenever a solid target is struck by a high-speed stream of electrons, those same little negatively charged particles of electricity which make our radio tubes work. In early X-ray tubes, the electrons necessary to produce the X radiation were released by first breaking down a small amount of air or other gas in the partially evacuated tube with high voltage applied between the terminals. Operation depended upon the amount of gas within the tube, and since this was variable, the tube was unreliable. In the present day hot cathode X-ray tube, of which this is one of several different types, there is a high vacuum, and the production of electrons depends only on the size and temperature of an incandescent tungsten filament with a cup-shaped structure surrounding it. This particular tube has two filaments, either of which may be used. The swarm of electrons, which is liberated or boiled off from the white-hot filament, is speeded up to a very high velocity by high voltage applied between the negative electrode or cathode, which carries the filament, and the positive electrode or anode, which is called the target. The electron stream is focused to a very small spot on the target by the cup-shaped cathode structure. It seems that the electron stream striking the target at terrific velocity is stopped so violently that the electromagnetic radiation known as X-rays is produced. The efficiency of X-ray production is very low, and most of the energy of the electron stream goes to heat the target. This heating effect of the electrons may be likened to the flame of a blowtorch striking a metal plate, while the light coming from the heated spot on the metal plate target corresponds to X-rays coming from the focal spot on the target of the X-ray tube. As a matter of fact, X-rays are like ordinary light, except that they are of very much shorter wavelength and are therefore invisible. Although X-rays themselves cannot be seen, their effects can fortunately be made visible. Photographic film in general is sensitive to X-rays, and a special type of it is used to record their presence. Recording of X-ray images on film is called radiography, and the finished films are known as radiographs. X-rays also have the power to make certain chemicals fluoresce, that is, give off visible light. A piece of special cardboard coated with one of these chemicals constitutes the so-called fluoroscopic screen. The use of such a screen to reveal an X-ray image is known as fluoroscopy. It has the advantage over radiography of enabling us to visualize internal structures in motion. Besides being of much shorter wavelength, X-rays also differ from light rays in that they cannot be focused in a camera. So ordinary photographic procedure cannot be employed. Instead, we use a shadow technique. If I now turn on this small spotlight and place my hand in its beam, I can cast a shadow of my hand on a white card. Now, if instead of the spotlight I use an X-ray tube, such as there is in this little portable X-ray unit, and if instead of the white card I use a film in a light-tight holder, I can cast an X-ray shadow of my hand, which on the developed film looks like this. Note, however, that instead of a solid silhouette shadow, as with light, the X-rays produce a shadow which shows a distinction between the bones and the flesh. In other words, X-rays pass through some substances more easily than through others, and the details of the image depend upon the amount of X-ray getting through the different substances which make up the object. It is this ability of X-rays to differentiate between types of substances which gives the rays their great diagnostic value. It seems both incredible and paradoxical that rays which are themselves invisible can reveal objects which are otherwise also invisible. But that is exactly what X-rays can do. It is then no wonder that X-rays have, in less than half a century after their discovery, become so useful in medicine and industry.